Hey, what's up, everybody? Good morning, good evening, or whatever time zone you happen to be in all across the world, or more than likely just here, the Moncton High School family. I want to welcome everybody to Sketching Polynomial Functions, which is essentially the final section that we do in this polynomial unit. I've broken this up into 3 separate videos, and then we're going to take a look at something else after this. All right, we're really in the last week or so of this unit, and we're going to get started here with some review first of all. So one thing that you definitely want to do in this section is you want to have your end behavior page. You want to have that handy. You want to have that either committed to memory, or more than likely you just wanted the information on a page next to you somewhere so that you can look at this over the next week or so, because end behavior is one of those things that we looked at. We divided up into cases of positive even, positive odd degrees, and so on, and the different situations that happen. End behavior, of course, once again, it tells you if you look at the degree and the leading coefficient, whether it's positive or negative, those two pieces of information will tell you in which quadrant the graph begins on the left and ends in the right. So you want to either go back to the end behavior video if you need those notes, or you can have, if you have the notes in front of you somewhere on paper, you can put that to the side and kind of use that as reference. Okay, we're not going to use it immediately, but it's definitely going to come up. The other thing I wanted to mention is something a little more recent. Okay, let's just remind ourselves the differences between factors and roots. And roots, of course, mean x-intercepts. Because we're getting into graphing, you're going to see and hear the word x-intercept a lot more than the other terms that mean the same thing, like roots and zeros, because x-intercept is directly related to the graph. And of course, factors and x-intercepts are opposites of one another. So the example that I have up here on top says that if the root is x is equal to -5, then the corresponding factor for that would be x plus 5 in brackets. Okay, so we have roots and factors are opposites of one another. The factors are what you get when you do all the algebra to break things down into factors. And then the roots, the opposites, you're going to use to sketch the graph. Okay, and then something new on the bottom here. Okay, this is all brand new. All right, we once again, roots, same thing as x-intercepts. And you can see on 3 of these graphs that there are x-intercepts on each of those 3 graphs. However, each of those roots have different types of multiplicity. Okay, multiplicity references the type of x-intercept that we have, first of all. Okay, so not even looking at the algebra or the equations or anything, just visually on its own. You can see the first graph on the left has 3 x-intercepts, and each one of them has multiplicity 1. What that means is that visually, what that means is that the graph just cuts to the x-axis. It's just your normal x-intercept, your standard x-intercept that you're used to seeing in most situations, where a graph just intersects an x-axis and that's that. Nothing special about it at all, just cuts through, and you can see visually that that happens 3 different times on the first graph. On the middle graph that I have here, okay, we have 2 x-intercepts. And then this x-intercept on the left, right here that I'm pointing to, okay, that one has a multiplicity of 1, just like the graph on the left. Okay, you can tell by looking at that x-intercept, it just slices through the x-axis in a normal type of way. But then the second x-intercept that I'm pointing to right here, okay, you can see that this x-intercept is a little bit different. You can see that it doesn't really cut through the x-axis. It hits the x-axis and then bounces back up. So if a graph touches the x-axis but doesn't cut through, it bounces off of that x-axis and back in the other direction, then it's still an x-intercept, but that is a root or x-intercept with multiplicity 2. And then the third graph over here, okay, we have 2 x-intercepts. Again, the one on the left that I'm pointing to right now, that one is a regular x-intercept with multiplicity of 1. But the one on the right here is different than the previous 2 types. We call this a multiplicity of 3. And the reason why we call it multiplicity of 3 is it doesn't just cut through the x-axis like most x-intercepts do, the multiplicity 1. And then it also doesn't bounce off the x-axis like multiplicity 2. This one more so kind of slithers through the x-axis. So it's kind of like a snake shape, like it's just slithering its way through the x-axis. So it kind of does this little slither thing. Or maybe you may refer to that as half of a chromosome. Maybe like a slide at your favorite water park or something. Maybe you have another type of shape in mind that it represents. But you can see that that type of shape is different than the other two, where it bounces if it's multiplicity 2 or just simply cuts through when it's multiplicity 1. So those are the three different types of roots that we are going to study in this final section. And again, you could actually have multiplicity 4, 5, and to infinity, really, but we're not going to study those ones. We're going to stick to 1, 2, and 3. Okay, so you've seen visually what these types of intercepts do. Now we're going to take a look at Desmos and look at an equation and then look at its corresponding x-intercepts. So what I have right here, okay, if we take a look right here at this, notice I have a polynomial on the left side here in the equation bar. I have a polynomial that is in factored form. So it's already factored, which is a lot of the work that you end up having to do, going through factor theorem, synthetic division, and everything. That's already done in this example. It's already factored, and you can see that there are 3 single factors. None of these factors are repeated. They're all 3 separate factors, and there's no exponents on the brackets. So these are all factors that give you roots with multiplicity 1. And remember, the x-intercepts are the opposites of the factors. So if the factors are x plus 2, x minus 3, and x minus 1, then you would expect the x-intercepts to be the opposite, which is x is equal to negative 2, which you can see on the graph. That's one of the x-intercepts. Positive 3 is an x-intercept, the opposite of x minus 3. And you can also see if x minus 1 is a factor, you would expect positive 1 as an x-intercept. So this right here is a degree 3 function. We know it's a degree 3 for various reasons. Okay, you know it's degree 3 because we have 3 factors. They're all degree 1. All right, there's no exponents on any of them. So that gives you x to the 3. You could also look at the graph and see either 3 x-intercepts, or you can look at the graph as it moves from left to right, and you can see that it goes up, down, up. So that's 3 degrees. Now, why don't we just experiment with this equation? Let's see what happens to this graph if I put an exponent of 2 or 3 on any one of these factors. So let's take a look at this factor of x plus 2. Okay, that represents the x-intercept of negative 2, by the way. Okay, what if I take that x plus 2 and I put that to the power of 2? Look how it changed the corresponding root. Now, the corresponding root, the root that it corresponds to the factor x plus 2, is the x-intercept of negative 2. And notice now that I have it to the power of 2. Notice that the graph doesn't just slice through the x-axis. Now it bounces off of that. That's a root with multiplicity 2, and that's represented by the exponent in the corresponding factor, the exponent of 2. So you can expect, if I go now and I change that 2 to a 3, you can expect a sort of a snake shape on the x-axis rather than a bounce. So let's take a look at this. I'm going to replace this with a 3. And check this out. Okay, you can see right here at x equals the negative 2. You can see right here that this has like a slithering shape to it, a slide, a chromosome, half of a chromosome, or various other shapes that you may consider that to be. It kind of slithers its way through the x-axis. It doesn't just slice through directly, and it definitely doesn't bounce. So that would be a root with a multiplicity of 3, and that is represented in the factored equation with an exponent of 3.